Hello everyone, myself Monu from group number 322. Today our topic is coupling of chemical reaction to transport of matter. The organism and the cell are chemical machines that operate as a result of chemical reaction and transport of matter between the cell and the surrounding medium and also inside the cell. This transport occurs in a certain definite direction perpendicular to the cellular and the intracellular membrane. The flux of matter is a vector. At the same time, the rate of chemical reaction is scalar, as has been pointed out. The direct coupling of scalar and vector process is impossible in an isotropic system by virtue of a Cure principle, nor it is possible in an isotropic system having a center of symmetry. Biological system in which chemical reactions are coupled to diffuse, namely membrane, are however made up of chiral molecules which have neither a plane nor a center of symmetry. Biological membrane are anisotropic. In such system, direct coupling is in principle possible. The vectorial coefficient LSV is equal to LVS may be different from zero. No theory of direct coupling between chemical reaction and diffuse in membrane has been worked out so far. One can visualize, for example, the transport of some reaction participants along the Crook channel in the membrane in which the center are located. Then the course of the reaction will be different for substance supplied from the opposite end of the channel. The same result is contained by considering a systematrical channel in which asymmetrical reaction centers are regularly arranged. There is, however, no ground so far of the stating that these effects are considerable. The uh, interplay between chemical reaction and the transport of matter can also take place by way of indirect coupling which arises due to the steady state condition. In the sta- stationary state, the irreversible processes that are not directly coupled because become interlinked. Let us return to example consider on page this along with substance that participate in the reaction. We shall introduce into the system as an inert substance Q which will not take part in the reaction. If the transport of this substance is however coupled to the transport of A, then this equation then this TV is equal to this. The last equation refer to the overall chemical reaction A to F from the steady state condition. It follow that this equation you can see we obtain this equation. The affinity this of the inert component is different from zero and proportional to the rate of chemical reaction in which substance Q does not participate. This reaction gives rise to a difference in concentration of substance Q inside the outside the system. You can see this equation. This provide an indirect coupling of the arrangement of substance Q to the chemical reaction. Let us consider indirect coupling in the general form. We shall write the dissipation function for a system in which a transport the generalized force is the chemical potential gradient and chemical reaction take place. You can see this equation. In the continuity condition for the ith component is this equation. The steady state condition, i.e. the constancy of the concentration Ci is equal to 0. You can see this. Substituting equation this into equation this, we found that this equation we integrate this for a one-dimensional flow along the x-axis from x equal to 0 to xa. The total dissipation per unit surface area is equal to this equation. An analog integration of delta ji yield this to, you can see this equation from to last equation. It follow that this or this equation, the sum in the last term on the right hand side of these expression represent the value of reaction affinity at the membrane bound arise x is equal to 0 and x equal to a for the component that penetrate into the membrane passing to the phenomenological equation. We write this equation J total chemical to this. You can see the microscopic eye integrated experience now contain of diagonal coefficient L I can this, but are they symmetric? The local unitrate expression do not contain of diagonal coefficient for the chemical reaction and diffusion. Since the system is isotropic and the Keough principle is valid, to put it differentially like this, and this where Le are the local phenomenological coefficient, the same referring to the inverse expression. You can see this equation. Let us found the relation between the local and microscopic coefficient. Applying the operate delta to the first equation, we obtained this. Substituting the steady state condition, we found that we multiply both sides of this equation by yve and carry out the summation over I. Since this we obtained this equation, we have obtained a differential equation for the coefficient at the this has the dimension of centimeters per cube per square. We designate it by lambda minus 2. Lambda is the relation's length. We have this. The solution of this equation has the form this equation. In order to pass over to microscopic experience, we have to integrate the local relation. Integration of equation this to from x0 to x gives this equation. Substituting this equation and integrating, we arrive at the following expression J. This equation, on the other hand, the equation of to equal this, the left hand side of this expression is equal to this equation. We substitute this expression into equation this and integrate from 0 to a. Since we found this equation,